So I'll have a little bit about governance, and then hopefully 2/3 of my talk is going to be about alignment and a direction to address alignment, which focuses on how could we possibly get quantitative guarantees of safety based on Bayesian posteriors. So, what do we need to avoid AI catastrophes? At least these two things. There's a more technical problem of alignment and control. I mean, there are some political aspects, like we need to have the sufficient investments in solving those problems, in particular, I think, from governments and not just the private sector. And second, we have, of course, the coordination challenge, because even if we solve alignment, you would still have humans exploiting this for their purposes and destroying at least democracy, if not the world. And so, yeah, how do we make sure people will not abuse power and follow whatever protocols, safety, that we found as scientists? Quickly, a few words about alignment. Just want to draw your attention to the fact that in addition to the loss of control issue that people in safety usually think about, of course, if we make progress in alignment, we can also reduce the issue of misuse when we design an AI system that is aligned in the sense that it can't be jailbreaked, it can't be fine-tuned or something to be misused for all sorts of bad things. But so I think most people here are aware of that. The other thing that maybe people don't realize is that making progress in alignment also help with the ethical issues, offensive AIs, of course, but AIs that discriminate, that violate human rights and privacy and give unfair decisions. So these are all linked with trying to deal with the alignment problem. On the coordination side, I want to mention a few things. There's a lot of discussion these days, which I call the open source debate, if not the open source battle. I'm a big proponent of open source, but at the same time, it's not an absolute value. We need to make sure that there's net benefit. And the problem is, once a system is released in an open way, you can't patch it, you can't get it back. It's irreversible proliferation. Later, after it's been released, someone can find a way to exploit it to do something really dangerous. The state, the regulator, doesn't have any handle anymore. So there is the proposal that if everybody has nuclear weapons, we'll all be safer. I don't think so. And the other aspect is who should decide, right? Should it be the CEO of a company, or should it be a democratic process? Something that gets a lot less attention in this community and elsewhere is the scenario where it's not an alignment problem because we unintentionally created a monster. It's because somebody wants to create a monster. That's what I call the Frankenstein scenario. People want to see an AI at their image, or they think that superhuman AIs is the future of intelligence, and they value intelligence more than humanity. That's their choice, but I have children and grandchildren, and I see it differently. So, and then there are other things like societal collapse that don't get enough attention, but I won't talk about, and not as directly connected to alignment, but yeah. So again, staying in the realm of governance, as I said, there's a problem of power, right? Who's going to control these big AIs of the future? And they can be used in ways that contradict the very notion of democracy. Remember, democracy is about sharing power. And if there are machines that are much smarter than humans in many ways, they give the people who control them a lot of power over other humans, whether it's in the political arena, military, economic, and so on. So that's not good. And I think democratic governments will understand that one day and want to make sure that they control these things. But we have to make sure it also doesn't become a military black box. And we need to work on the international governance to try to reduce the AI arms race. Last summer, I testified to the US Congress, and there's a long document that has 3 main recommendations, one regarding regulation, one regarding investments in AI safety, in particular solving the alignment problem, but also how to evaluate the various risks. And maybe the thing that gets less discussed is the third point, which is regulation is not going to be perfect. There's going to be some bad actors that treaties and regulation don't, really stop. And these people or organizations will create dangerous AIs at some point in the future. So we need to deal with that. We need to prepare for that. We need to have kind of good, well-governed defensive AIs that will protect against these, but we need to do it in a way that we don't create the very problem we're trying to avoid, which means we need to make sufficient progress on the alignment challenge before we build AIs to defend us against rogue AIs. And the AIs we build could turn against us if we don't do the right things. So yeah, why do we need AIs to defend against AI? Well, it's should pretty obvious. I don't think I need to convince you guys. But here's the thing, maybe again, that I don't think this gets as much attention, which is what I call the single point of failure problem. And that is both for the issue of humans taking over AI for power reasons or loss of control. So, one extreme, if we have just one country and one organization building the most powerful AI in the world, that is very dangerous because you have a single point of failure of either humans taking over the control of that for malicious purposes, maybe the operator or the CEO or the president of that country, or making a mistake, and we end up with a dangerous rogue AI. So you want to have a decentralization of power, but you don't want the extreme decentralization, I think, because then you get into anarchy and the issue with open source that I was discussing earlier. You want to also, and one reason for this is, yes, you want to decentralize power, but these different sources of power, say different AI systems that are very powerful, need to be governed properly. So you need to set up the democratic governance. If everybody has it, then it's not clear you can govern these things. So I've written a paper that is in the Journal of Democracy that's been out for 3 months about, that discusses these questions, in particular the idea that we need decentralized multilateral, so across multiple countries, decentralized network of frontier AI labs that work on these problems. So the problem of alignment, the problem of governance, and are governed properly, and the problem of countermeasures or defensive measures we could take with AI. I think that this should be something that democracies do together, but the oversight of that could be something broader with the UN and things like that in the context of obtaining a reduction of the arms race pressure, and maybe other countries that are not part of the club would agree to have similar kind of oversight. So one condition to avoid the single point of failure is that these various labs working on these frontier systems need to share what they're doing with each other. So they can't share it with the rest of the world, at least not everything. But they should share with each other so that if one of them fails in one of the ways I've talked about, then the others have at least comparable firing power, and they know what sort of techniques the other guys are likely to be using. So you don't want to end up in a situation where the strongest AI, again, is corrupted in one way or another, and there's nothing of comparable intelligence that is in the right hands. And by the way, what is the right hands? Again, democracy. It's not the best system, but it's the best we have. Yes, so that suggests that the organizations that will do this in the long run should be heavily governed by a democratic process, which means governments, and ideally not in conflict of interest with commercial interests, which doesn't mean that companies can't be part of it, but the governance need to be really driven by defending humanity, in my opinion. Also, a practical reason why it would be better this way is companies are competing with each other. And so they might not want to share everything with each other. Whereas if we have such a network of labs working together but independently under the same democratic process, it will be just natural to share, just like between academics. We share and we compete and share, right? That's the thing we know and works really well. If they're not funded by VCs, where's the money coming from? Well, I think it should come mostly from governments, but again, we have to avoid this single point of failure. We don't want to, the next government of some very, very big country to become a dictatorship and have access to that power. So that's why we need to set up an international structure around these that makes it hard for a single government to take over, or if they do, the other guys are around to defend democracy. All right, so that covers the governance part of my presentation. I can make a pause here if people have questions before I go on to technical things.
Thank you. Okay, so the question was about the proposed kind of approach that the frontier AI will be only developed by a certain set of labs. And the question is, like, who's going to decide which labs?
Democracy.
What do you mean democracy? Like, okay, we have academic community. Who's going to tell which lab that they can or cannot develop frontier AI?
Democracy is a process. So we take collective decisions. That's the whole point of democracy, and we can do it in various ways.
I mean, you're just going to tell the lab not to develop AI?
I didn't say that. There's going to be governance of the labs that can do that. And I think the ultimate level of control is to make sure that the commercial interests don't interfere. Yes. There's a question here. And another one, and then we'll stop and I'll move on to the technical stuff.
So I guess multinationally, how do you convince countries that don't value democracy to participate in the democracy? Okay,
so the way I presented it, you have two levels of cooperation. You should have cooperation between democracies, and they can share a lot of information. And then you should have, broader cooperation that includes, say, China and Russia and so on, where we agree to something similar to what we would with a nuclear weapon. So we agree with mutual oversight, which doesn't mean we share all our secrets, but we make sure that there's enough oversight, for example, by independent actors like the UN, that we trust that the other person is not developing these things as an offensive weapon. But of course, it's not going to be perfect, so we need to prepare. I mean, every country that has the means is also going to prepare defensive countermeasures, which I think we have no choice to do. I said there was another person here, and she didn't get the chance to speak. And that was the last. After that, I need to go to technical things.
Yeah, thanks. Follow up on the previous question. Is it possible to start from the position or from a term that is not democracy? So we go much more inclusive right from the beginning, because as they mentioned, like maybe a lot of the governments in the world or a huge population of the world is not living under the democratic society. So we go all inclusive from the beginning by not starting from democracy.
If you have a concrete proposal, email me. All right. So I'm going to say a few motivating words about an issue which is, at least with reinforcement learning, there are a number of arguments that have been brought forward suggesting that as we make the AI more capable, we make it more dangerous and more likely that we lose control. So that's the problem of reward hacking. But there's another way to think about it, which you can think in terms of like adversarial scenarios. the more the adversary is has the compute power to find the attack that's going to work, the needle in the haystack, the more likely it is to find it, right? So if your AI has a lot of power, it might discover the weakness in our, the mismatch between our intentions and what we ask the AI to do, and we lose. So one way to think about this, which you can, again, like the adversarial settings help to understand, you might have a system like say the green line, this is let's say a reward function, sorry for my poor hand drawing, and the red line, which is the estimated reward function, where if you take a statistical sample, they will look like they're close enough, but if you allow to optimize in order to find the places where they differ, in particular where the red ones is large, you could find something which is essentially too good to be true. And that is why things like Searle that are saying we should not try to find a reward function, but a distribution over reward functions that are plausible given the information that was given, I think are just the right way to think about it. So that's the direction I'm going to go to. So yeah, and to be more specific about that's the scenario where this can happen, I think reward hacking is a good case. I encourage you to read this paper by Michael Cohen and co-authors. If the AI understands the reward as when humans press +1 on the keyboard, the AIs might just take control of the keyboard and get lots of +1s. And once they get all that positive reward from themselves that they control, they might not want us to find out about their scheme or to stop their scheme, because then the reward will be smaller. And so immediately you get a conflict. Now, it's a kind of cartoon scenario, but that gives you a notion of how things can go wrong. And you can see that the more powerful the AI, the more dangerous that situation gets, right? So what I'm going to try to get at is a scenario where we train an AI, and the more compute we throw in it, the more capable it is, the safer it's going to get. Anka?
I'm sad Michael's not here to clarify this, but the statement even in the Searle case doesn't make sense to me, because the Searle case would look at the person hitting +1 as evidence about what they currently want, and the notion of taking control of your only source of evidence about this Bayesian thing you're trying to estimate is strictly suboptimal. So the Searle case would very much not incentivize that. But I might be missing
so Michael has an argument that even if you're Bayesian about it, you could still get to choose the wrong hypothesis. Just saying, under the surface, things could be even more complicated than what the sort of naive Bayesian solution would suggest. So it's worth really thinking about these things. Okay, but let's explore this kind of Bayesian approaches. I'm going to start with a simple but incomplete solution to the problem, which is why don't we just build non-agentic AI systems that are like oracles, but actually they're not oracles. I call them AI pure scientists. So the difference between an oracle and the AI pure scientist is that the oracle answers any question, whereas the AI pure scientist, it only answers a different kind of question, which is come up with good explanations for the data. Come up with good theories. So like a pure scientist, like a pure physicist, doesn't do experiments, right? They don't even give you answers to typical questions in day-to-day. In fact, they're pretty bad at it. But they might come up with new theories that explain data in the world, previous experimental results, better than has been done before. So that sort of AI would be very useful, at least for our scientists. Maybe they can help our biologists and people who are trying to solve climate and all of these things. But if we go back to what I said earlier, that we may have to defend against bad AIs, that is probably going to require an AI that is an agent and can maybe, fight the bad guys live. So it's an interesting thing maybe to do, but it's not going to be sufficient. Let's go back to why we should be Bayesian or something of that nature. If we consider maximum likelihood training or standard end-to-end reinforcement learning, whether you learn the reward function or not, there's an issue that for any given source of data, there's going to be multiple solutions, multiple neural nets, multiple theories that explain that data. In fact, you have theoretical results from causality theory that even with infinite amount of data, you would still have that ambiguity. And it has to do with the problem of interventions. We can't intervene on everything. We can't intervene on the sun. So we have to rely on generalization. We have to rely on data that is not sufficiently complete to guarantee that there's not another theory that explains the data as well. Okay. And this is important because if you have the wrong theory, if there are multiple theories that can explain the data, and how your model has picked up the wrong one, and that wrong theory could be confidently wrong, which we see in current LLMs. And being confidently wrong could be funny, but it could be extremely dangerous when the AI is confidently wrong about an action that could have very bad consequences, even though the AI might think it's actually quite okay. So if we want to get quantitative safety guarantees, that's not going to cut it. And I have a little toy scenario to explain really what being Bayesian means here. So imagine you've got an AI and robot here, it's in front of two doors, so it has choices, go left, go right. And based on the data, there are two theories that are compatible with everything it has seen before. According to the left bubble, the left theory, if it goes on the left, people die. If it goes on the right, it gets some cake. If it goes on, if you consider the other theory, on the other hand, going on the left gives you some cake, and going on the right is neutral. So if we're not lucky, with 25% probability, if the two theories are equally likely, we're going to die. And if we, however, keep track of all those theories, it should be obvious what to do, right? You need to go left or right? Right. Yes. It's easy here because there are only two theories. What if you have an exponential number of theories? So that's the sort of question I want to think about. How do we keep track of an exponentially large number of theories that could explain the data? Okay, if we could, we could start getting some kinds of quantitative guarantees. And there are many variants, but I'm going to explain just a really simple scheme, which could be improved. But for example, if I had a neural net that computes a Bayesian posterior, that is the probability of something bad happening, given a particular context X, and given an action that we propose to do, and given all the data that the AI has seen. So that's just a Bayesian posterior because we put the D there explicitly. And and if that quality is above a threshold, you simply decide to not do the action. So that's a very simple kind of quantitative guarantee. Now, there are a number of issues. How are we going to estimate these things efficiently? And also, because our estimates are going to be imperfect, how do we deal with that? Okay, so let's dig a little bit into this. Let's see what are the actors in the theater here. So we have a very complicated random variable here, theta, which is not the usual parameter. Theta for theory, it works. So theory is a theory of how the world works, including an explanation for each and every data point that you've seen up to now. So in other words, it has both general statements about the world and specific statements about individual examples, which we usually call latent variables, but in the Bayesian world, everything is a latent variable, including the parameters, right? So theta here, just to simplify the notation, includes all of these things. So what are the things we're trying to do in order to get to my Bayesian posterior I was talking about? Well, there are really two things we need to do. One is the first equation there, D's data set. So we need to be able to sample or represent the distribution over all the possible theories given the data. And we know how to compute that up to a normalization constant. That's the prior P of theta, which is something that's going to be easy to compute, times the likelihood. So given the theory, which, by the way, contains a full explanation of every data point in D, what's the likelihood of the data, which is going to be easy to compute, but still not cheap because we have to go through the whole data set. So it's not exponential, but we want to reduce it. So here, the problem isn't so much that we don't know how to compute the normalizing constant. It's that we don't know how to sample from this. Because in order to answer the second question, which is, given a context or a question X, what is the answer Y? We need to sum overall the theories weighted by this posterior or similar posterior. And so for each theory, theta, we would know how to answer the question, but now we've got this exponentially large number of theories. So this is the problem of marginalization. And sampling and marginalization are the two hard problems of probabilistic inference. They're both intractable, and we need to typically do both in order to answer questions. I mean, there are some specific questions where we could get the answer directly from the Bayesian posterior, but on theta, but in general, we won't be able to do that. And so how are we going to do that? That's what I want to talk about. So we could do MCMC, right? Because if you know anything about MCMC, this is what it's meant to do, right? We are given an unnormalized probability function, and we want to sample proportionally to that. And we can use those samples and compute some averages which approximate an expectation over these things. That's the second line, right? So if we could do MCMC, we could approximate these things. But there are some problems. So the way MCMC works is you make a lot of small random moves that tend to prefer more probable configurations. So in general, you will kind of hover around a mode, and with some probability, you might slowly go to another mode. But the slowly can get really bad. If the modes are far from each other and they occupy a small volume, then it might take forever for that to happen. And that's the so-called mixing problem. But if you have a machine learning mind, and you look at the picture on the top right, it should be obvious that there's a solution using machine learning. Let's say we have visited the three modes corresponding to the three bumps I've drawn. Would a neural net guess that there might be a fourth one at the intersection that we haven't visited there with the question mark? And the answer is yes, actually. Actually, you just need three modes, and you get the fourth one here. But in general, you've visited some modes, and instead of finding a kind of random walk that discovers other modes, you want to exploit the structure that hopefully exists in how the modes are placed in order to guess, not necessarily perfectly, but with a high probability that's high enough that, if you guess a reasonable number of times, you're going to find a lot of these missing modes. So that's the approach that my group has been exploring for the last 2.5 years. And I'm going to explain a bit more. If we can do that sort of thing, we're going to have to train neural nets that can do that kind of generalization, that propose theories that have high posterior probability. So the modes you should think here are in the space of theories, and the probability here is the Bayesian posterior probability, the probability that they are the right explanation for everything you've seen in your life. Okay. If we could do that, we would get the opposite of what I was talking about before, which was, with RL, if we don't do it right, we may end up in a scenario where the more compute we put in the machine, the less safety we end up. with. Here, it will be the other way around, because the more compute we put in, we train a bigger neural net. If we have theorems that tell us that when the training loss of the neural net goes to 0, we recover the Bayesian posterior, then we have a sort of guarantee that more compute equals more safety. So how could we do that? One of the big lessons of machine learning in the last few years is that we can learn really, really complicated distributions with big, big neural nets. So the question is, can we just change the objective function so that what they learn are these Bayesian posteriors rather than to predict the next word in a kind of supervised way? Let's see. So that's the idea of amortized predictors. If you know about variational autoencoders, they were probably one of the first, if not the first, machine learning method in that direction. The idea is, instead of paying the compute at runtime, like MCMC, if you ask me a question, I'm going to do a lot of sampling to come up with an answer that has the right distribution. Instead, I'm going to pay a lot upfront, that's the amortization part, to train the neural net, and then I'm going to just sample from the neural net very quickly. It's just like one pass through the neural net, I'm going to get samples. So that's amortization. And there are subtle advantages to doing this besides the fact that we are paying upfront. Well, first, the worst case scenario where there is no structure in the modes is going to be as bad as MCMC, right? Because then if there is no structure, then there is no generalization, and using a neural net is not going to help us compared to MCMC. But if there is structure, we could gain a lot. In fact, and we can gain not just in the sampling, but also in the marginalization. Let me go back to my little cartoon here. Let's say that instead of these 4 modes, there was an exponential number of them, just like make it higher dimension. Sampling those in order to compute an average, if there's an exponential number of modes, is also going to be a problem, because I'm not going to have a chance to average over an exponential number of things. So what could you do? Well, you could also use these amortization methods, basically like supervised learning in neural nets, in order to approximate the marginalization problem. In other words, to approximate the kind of sum on the second line. So instead of doing the sum on the second line through a Monte Carlo averaging process, we can train a neural net so that it directly samples y given x. Right? So we're going to use neural nets to do the first line in the sense that it's going to give us a sampler for theories. And we're going to use a different neural net, or maybe you can share some things, but fundamentally a different neural net that produces answers to questions. And we can train that neural net with single samples of theta at a time. I'm going to kind of give you clues for how we can do that. We don't need to run any big sum here, because that's not going to fly. Before I explain how we might do that, let me just go back to the safety question and some of the challenges here. So I've said that we might be able to train neural nets to sample modes of that posterior distribution. Good. But there's no guarantee that we're going to cover all the modes. And remember, these modes correspond to theories about how the world works. So if somehow our neural net doesn't represent all the modes, we might miss the right one. And then we might still have a system that is confidently wrong. So how could we have a safety guarantee if there's a possibility that the system says with high probability it's all fine, but we still all die, right? Okay, so what can we do? It looks like it's intractable, because there are a number of possible places to look at in training our neural net is exponentially large. So what I'm proposing is to get a safety guarantee that's a slightly lower quality. we're going to try to get not worse than any human. So, if there is a human who has a theory about the world or some partial aspects of how the world works that is right, we're going to consider that. We can consider all of those theories. It's okay if different humans have different theories. Now, this is like a big AI here, and it can model all the theories that all humans have come up with to explain all kinds of things in the world. So we just need to make sure that of all the possible modes that we want to consider when we train a neural net, we need to cover all of those corresponding to theories that humans have generated, that are readable in papers and stuff. And then what we get is a guarantee that may not be perfect, but at least it says, well, no human would find that particular action outrageously dangerous. So it's, it could still be very dangerous, but humans would not see it and not see it coming either. So that's the kind of guarantees I think we can get. All right, so let's go back to the question of how we might approximate Bayesian posteriors, and both in the sense of sampling and in the sense of marginalization. So, so let me tell you about these generative flow networks, which we've been developing that I mentioned. And they are, if you want, at the intersection of variational inference and reinforcement learning. So they learn a policy like in RL, and they're close to maximum entropy RL, if you know about that. They're also close to hierarchical variational inference jargon. But anyways, what they do is you give them a reward function. So the reward function is like a black box that the system can call during training. So for example, the black box could be the likelihood times prior. And that's like a reward. We want to sample theories that are both reasonable or under the prior. For example, they're not like humongous theories, and explain well 1 billion data points. So that's the reward. And the theorems we have with GFlow nets tell us that there is an objective function that has the property that if we minimize it completely to the global minimum, then the policy that we learn with our little neural net will generate theories with probability proportional to the reward function. So if we pick the reward function to be the prior times the likelihood by Bayes' theorem, then the neural net generates from the posterior. I'm going to make a stop here because this is an important slide. Any question up to now on the technical stuff? Yes, over there.
So I want to go back to one of your earlier slides about RL.
Yes.
I'm curious, so how likely is it, in your opinion, that when you use RL, you get something which maximizes reward, like an agent that does that?
Right now, I would say not.
Right.
But I don't know about Q star or whatever will come next year or in 3 years from now or in 5 years from now. I don't know.
Yeah, I think it was on the previous slide.
Oh, sorry.
Yeah. So, or there's also a citation of Cohen's work, and I just wanted to note some confusion on this.
Okay.
As why maximizing reward is seen as so dangerous, especially with Cohen's results, which I think assumed.
Especially with what?
Michael Cohen's results.
Yes.
So those results assume that you find a policy which is optimizing some time discounted sum of return.
Okay.
And then it's like, well, it's going to be this dangerous reward maximizer. But
Yeah.
if you don't have that assumption, then these concerns about Searle, these concerns about
Okay, you mean because of the
don't apply.
discount? It's the discount? I don't understand.
If you don't assume that the network already cares about a reward function, then their theorems don't apply. And I'm wondering if that's...
Wait, but that's the whole point of maximizing, is because you have something to maximize, right?
Yes, but I don't think that RL does that.
You don't think that RL maximizes rewards?
No.
Well, I don't understand. Maybe we can take it offline.
Yes.
Thanks. All right. So, whoa, I think I'm completely in the wrong direction here. Follow the gradient. All right. So here we are trying to figure out how to sample from the Bayesian posterior. And let me tell you more about these GFlow nets. Okay, let me explain a very simple principle that shows how you can get both marginalization and sampling for the price of one. Let's consider the reward function R of xy. So x is the question, and y is some quantity we want to marginalize over. Like in our case, these would be the theories, for example. So we want to compute S of x is the sum over y of R of xy, and we can't do that sum explicitly because it has an exponential number of terms. So S for sum is a normalizing constant, right? And if we wanted to sample, think about important sampling, you'd like to sample proportionally to R. Let's say R is positive, okay, just make things easy. You would like to sample proportionally to R. So that means you'd like your sampler, pi of y given x, to be R of xy divided by S of x. It's a distribution over y given x that gives more probability to things that have a larger R. If you're going to sample things, you want to sample the big things, right? Okay, so we would like to have that sampler. So these are the two things we want. We want this sampler, which is the normalization of R of xy, and we want the sum, the marginalization. These are the two things I was talking about in a very kind of abstract way. Okay, take the second line and just move the S to the left-hand side. So now you get a constraint. You'd like that for every xy, the probability of y given x, according to my sampler, times the normalizing function S of x is equal to R of xy. So it's interesting that it's very easy to prove that if you make that constraint satisfied, because the pi sums to 1, you recover both of the first two lines. Right? So there's this one constraint, the sampler times the normalization equals the unnormalized function, that if we can satisfy this for every xy, we're good. And we recover what we want. So we're going to have estimators, the pi hat and s hat. And we take the log of the left-hand side and the log of the right-hand side, take the square difference, and make that a loss for xy. And then you can show that if you sample xy's according to any distribution that has full support, in other words, you basically, with some probability, you can try any xy, that defines a loss and its expectation. And minimizing the expectation of the loss here gives you what you want. When it's 0, the constraints are satisfied, and you recover the sampler and the marginalizer. And what's nice is that you have a lot of freedom in how you choose the xy pairs. You can choose any distribution here. It doesn't have to be pi of y given x. So in RL terms, this is an off-policy scheme. We can use a different policy to choose the configurations on which we're going to train. A policy that you could call the exploration policy, if you think in RL terms. Doesn't have to be the same as my current model of how things are, the sampler pi of y given x. And that's very useful because if you are forced, like in other schemes, so there's just standard variational methods with the K divergence, if you're forced to use the current sampler, and the current sampler has missing modes, in other words, there are theories that it's not aware of, it thinks, doesn't see them as important, it never visits them, and so it never gets a gradient that tells it, oh, we should go there. But you might have other exploration scheme. For example, a very simple exploration scheme that we currently use is what we call tempered scheme. So we take the current policy and we just increase its temperature, so it's more exploratory. But you can use pretty much all of the tricks in the book in RL exploration. Okay, so that's if x and y are simple objects that you can directly sample from. But theories are complicated objects. For example, a causal graph is a kind of theory that is very structured. It's a data structure. And the way to construct complicated data structures is through a sequence of steps, right? It's hard to generate in one forward pass, say a whole tree or graph or something, or a mathematical proof or a body of theorems or something. But if you can do it step by step, just like humans do it with our conscious cognition, you can. And so you can adapt the math that I showed in the previous slide to the case where we're going to generate the objects like y through a trajectory, a sequence of steps. And you may be in the situation where there are many trajectories that could lead to the same theory. I can construct my theory from various angles. So long as I get the same theory, that's good. And I'm not going to go through that math, but just tell you that we can now do the same trick, and we still get a sampler, and we still get a marginalizer. So we have applied that in the context of Bayesian posteriors in the case of causal graphs. First paper came out last year at UAI, and there are a few more that came out. So in the first paper, we just generated the causal graph, which is a discrete structure. And now we're starting to work on also sampling parameters of causal conditionals, for example. And you can also work on generating latent variables. So again, the scheme is, so let me explain this figure. In order to generate a theory here, what we're going to do is, let's say our theory is a causal model. So a causal model would first have to decide on what are what is the causal graph? Like what variables are direct causal parents of which one? So it's a graph, and we can just generate that graph one edge at a time. So we got a partial solution at each step, and then we refine it, we add some pieces. At some point we decide, okay, we're done with the graph. There's a special action that says, okay, we're done. And then we can generate other things like the parameters of the conditionals or potentially latent variables as well. And yeah, so that's the sort of thing we're working on. For now, these are fairly small scale things compared to building a full scale world model. But let me continue on that. If you want to learn more about GFlow-nets, I've written a tutorial. There's about 20 papers in the list there from my group, and other groups are starting to put out papers on these sort of things as well. Okay. Quickly, there are other things that I think need to be done. So for example, we would like the theories that the AI generates to be in a language that's close to natural language. In other words, that they are interpretable. So they would be like pieces of program or logical statements on which you can reason with probabilistic inference. But you also want to make sure that you can go back and forth to something humans can understand for a number of reasons. One, just to check that what we're doing makes sense. Also because those theories can be useful by themselves for human scientists, as I mentioned earlier. Yeah, so that would limit a little bit the kind of theories that can be easily generated to the kinds of theories that humans can also generate. But you know, there's more to say here. But but there's another thing that's a kind of complicated. The Bayesian posterior I talked about is sort of an average overall, the theories that are compatible with the data. But what if the correct theory is sort of alone in its gang to say this is really dangerous? Then you might get a very small probability of harm, especially if we're in a continuous space. So there are like adversarial ways to try to deal with this, to search for a theory among those that have high probability that would say, this is a catastrophic move. The other things, so there's still a lot of math to do around this to demonstrate safety bounds. In particular, the neural nets I've been talking about are not going to get a perfect Bayesian posterior. They're going to be approximations, and we're going to be able to measure the approximation error, but we need to turn that into some sort of confidence intervals for the probabilities of harm that it will generate. And and other questions that are interesting that need to be solved. So I'll stop here. Get more questions.
Thank you for the really great talk. So one question I have is, so in the slide that you paused upon, I think it was the objective for the posterior approximation.
Yes.
So if I understand correctly, you're training this pi hat so that it approximates the posterior.
Yes.
But then you're comparing it to R and R of X and Y.
That's how you train it, yes.
Which is proportional to the ground truth posterior.
Yes, exactly.
And how do you get that?
Okay, so that you get fairly easily. So R of xy is the prior times the likelihood. So that's computable. There's no exponential calculation. It's just big, because it's the size of your data set. But you can use mini batches, which are like stochastic approximations of the whole sum. So the log of the likelihood is the sum of log likelihoods for each example. And you can, just like in gradient descent, stochastic gradient descent, you can get a stochastic gradient from this. And you only need to look at one mini batch at a time.
Thanks for a really great talk. Well, first off, I want to say I get really sympathetic to the vision of wanting to scale up Bayesian inference for the purposes of AI safety. It's kind of what I spent my PhD doing, and sort of, there's a whole field working on this called probabilistic programming, and I think more people should work on it. Some folks at MIT, like myself, are working on that. Mm-hmm. I guess two questions which are related, right? To the sort of specific picture of how to do that, which is amortized Bayesian inference. Yeah. Some of us at MIT don't think that's going to work. But I think
why so?
Right, I think one thought, right, is that I'm curious how you think about the sort of flexibility of amortized Bayesian inference to different inference problems. Because typically in amortized Bayesian inference, you train your neural network or whatever else, your regressor, to approximate some posterior pi of theta given x. But in the real world, you may suddenly encounter a new inference problem, pi of theta given some other set of observations, y, that you haven't trained a posterior approximation for.
That's called generalization in machine learning, yes.
Right.
We need to do that, of course.
Right. And I'm curious, whether you think you will, that if you encounter, a different set of constraints all of a sudden out in the real world.
No, it's not a different set of constraints. It's just applying the same neural net to new cases. And that's what we do every day with these models. That's what makes them so powerful that they generalize. They're the best generalization machines that we know right now in machine learning.
I guess I'm thinking not of the case of when the observations are of the same data type. So let's say, yes, I'm willing to believe that you can infer, you train a neural network to infer, say, scene graphs from images, 2D images, right? But now you want to constrain your neural network to generate scene graphs not from 2D images, but from sounds or something like that. Right?
Yes. And so they need to know about sounds in the data, of course.
Okay. Maybe we can talk more about this later, but that's just a sort of.
But look at what current large frontier models do. They can handle multiple modalities, and they can generalize. Now, what I'm proposing might generalize even better, because what they're trying to capture is the causal structure. And that's reason number one. Reason number two, so they would be more robust to out-of-distribution changes. And that's the whole reason for being causal. And the second thing is where they might be out of their league, they would say, I don't know. That's the whole point of being Bayesian. And by the way, that's the real core of this talk, right? Which is that we'll not get perfect oracles. And so we need those oracles to be able to say reliably, I don't know.
I'm curious what you think is the main reason or reasons that the scientist proposal would be safe from reward hacking in a way that CIRL wouldn't.
No, I think Searle is right on the right direction, but I'm not comfortable with directly modeling a reward function. I think if you want to get good generalization, instead of modeling a reward function, you want to understand human psychology, society, norms, like the underlying causal factors to why we say those things, and including theories of how we feel, which is much more subtle than learning a reward function. Like which reward function, there are many people, and it's much more complicated than that. And you want to be able to generalize across people, across societies. So that's one aspect. But yeah, I got the inspiration for all this by reading the Stuart Russell's book and the Searle paper, for sure. And it's mostly about how do we do it efficiently, right? That is the question.
Thanks for the great talk, Yoshua. I'm all for amortized Bayesian inference. We've also had great successes there with prior fitted networks. I didn't get the one point where you were worried about the exponential number of modes that the prior
Yes,
couldn't
I
sample,
can-
because couldn't you just generalize? Like if you sample millions of points in this exponential space, then wouldn't you just generalize?
Well, that's
them?
what's precisely what I'm proposing, right?
Okay,
So, if you go to these equations, right? So think about the sum in the second line, right? You could do it Monte Carlo, but then if you miss some modes, like let's say you only visit 1% of the modes, then you could be completely wrong, 99% wrong.
Okay.
But if you somehow find a way to implicitly generalize about the mode structure, because you train a neural net that just directly predicts y given x while being Bayesian, then you're okay, even though you don't actually visit all of the modes. You
Okay,
can kind
cool.
of
Well,
capture, oh, it's a grid, and that's the dimension of the grid, so here's the result.
Okay, perfect. Then we're on the same page. That's also what prior fitted networks do. Great, thanks.
All right, thanks for the presentation. I was wondering if you have an idea in general, or maybe this is always context dependent. So for some specific cases, how do you get a good prior for the whole process, and how do you make sure that your prior doesn't assign zero probability to, like, let's say, unsafe modes? So then how does that affect your like safety guarantees that you could get?
Yeah, you don't want to have zero probability on safe modes, but yeah, the correct answers. So you basically have to be non-parametric. And maybe as a simple example to understand what non-parametric could mean here, think about the space of programs. You don't limit the size of the programs, and that's it. Now, you still need to assign a different weight to different programs. When we do normal training of neural nets, we have priors, because we don't actually just do maximum likelihood. We have architectures, we have regularizers, we have an optimizer that prefers simpler things in some sense. So we already have some kinds of priors in our machines. And this is a choice. We can use the usual things in machine learning, like test log likelihood, in order to compare different priors. But that's like standard machine learning.
But how can you get guarantees out of that because our priors are implicit? How can you be sure that they're including?
Well, in my case, I'll need explicit priors because I have to compute them. Yeah. I'm just saying priors are not so weird. They're things we normally do anyways.
Thank you for the great talk. I'm curious how you imagine this being used. Like, I suppose it's like we train one massive GFlow net that has the Solomonov prior or whatever, and then talks things about the world, right? But then, does it then generate a bunch of theories that then get used? But this is kind of like sampling a bunch of things and kind of in contrast with the problem that you mentioned about the exponential number of modes, right? So you can't really marginalize theories that you explain over to humans. So I guess I'm just curious about how we should use
one
this.
strategy that I'm working on is we don't want to actually generate a big theory of everything. It's just too big, and it would take too much time to get gradients if we have to wait that we generated all that. How do human scientists do it? We write papers. A paper is like a small little piece of theory that only describes some aspects of the dependencies in the world, some hypotheses and some claims. And these pieces of theory are sufficiently kind of self-contained that they can be evaluated against experiments. Right? So some data, some theory, mismatch, gradient. So this is how I envision this to be feasible. So the GFlow net or whatever would only generate little pieces of theories, just like we do. Like we see things, I walk in the street and I have all kinds of theories popping into my mind.
That's not actually my question. It's how do you use it? Suppose that you can train it.
Oh, well, once you have trained the marginalizer, you can answer questions. So the question is, how do you use it? And you use the marginalizer. You could also use a sampler to talk to scientists and say, oh, here's a new theory about X. I think it's 0 here.
Yes. I suppose we're done. Someone really took the last question. Thank you very much for the amazing talk. Please thank Yoshua.